Cool. Sticks and Stones Will Not Break My Bones by Oscar and Ty. So it starts with all saying, what is a transistor? That's how you define it. I'm defining a transistor. Face down 0, face up 1. Now, I originally wanted to start it with dominoes. So I originally tried to do some ideas of this one. This one, if either one of these get knocked, then this end part will get knocked down, and that constitutes a 1 value. This one, both have to get knocked down, because if not, then this one will block itself, right? So we can kind of see how that works. That's really cool. The not one, I had to cheat a little bit. I set a really long input right here, and I knocked it with another box. But then it only, for it to be blocked, I have to knock this input so that this can stay 0. And for the XOR, this one basically, if they both get pushed, they have to interfere with each other, and they won't move, right? And this concept can be used to make half adders. Half adders are basically things that add two numbers together. That's AND and XOR. And then fusion Ha, basically that's basically two half adders put them together. You make this thing called a full adder, which is add 3 numbers together, and then you get another thing out of that. So concept here, you take 4 full adders together. Basically, it's just like carrying over the ones, kind of like doing that math when you carry things. So that's what it does. Basically, put four full adders together, and you can add 2 4-bit numbers. And that's what Oscar did. So basically, he defined all these things. He defined NOT gates, SAME gates, AND gates, OR gates, XOR gates, and he basically took all of these, put it together so that you can make 4 full adders to make a 4-bit adder. And that's what I tried to make with a bunch of cards here, as you can see, right? So all of these are basically at 0, and when I flip them over, then they turn into 1, and I could notice the output on these little things. So these things basically tell me what the final number is. So if they're all flipped over, then it's 1, 1, 1, 1, 1. And this is a 2-minute demonstration of how I did it. Oh, let me share my audio actually.
So with a bunch of cards, I've made a 4-bit calculator, basically just using OR gates and AND gates, or XOR gates and AND gates. And since a 4-bit calculator adds 2 numbers together, these numbers are represented by these 2 cards. So if I flip this over, then it's considered a 1. If I leave it like this, then it's a 0. So I'm adding 2 numbers together. These represent the first number. So that's the first number. This is the second digit of the first number. This is the third digit of the first number. And this is the fourth digit of the first number. And that's how it goes, like this one. This one is the first digit, second number. First digit, second number. First digit, second number. Fourth digit, second number. And then it will add all together to put these outputs. So these are considered the sums. So that's a sum there, there's a sum there, there's a sum there, and there's a sum there, right? Now what's connecting all of these is what's called the remainder, right? So the remainder, I've put in this one, this long line right here, and the remainder gets fed into as input for the next full adder, and with a long shot, this is how it all looks. Basically, it starts here, goes down full adder, another full adder, another full adder, and then all the way right there is the last card for the end.
Yeah. So really cool idea, basically. And I think it's really makes me appreciate how like a lot of computers work, basically, because like yes, the concept with every little thing is very simple, right? If it's flipped over, then it'll flip over the neighbor. If it's not flipped over, it won't flip over. But the point is here is that, putting it all together, you can actually get a pretty complicated calculation. Now, it doesn't have to be this complicated. I did make it a little bit more complicated than it needed to be. Essentially, these little curvy lines represent, I think, like I call a spacer. So if I were to make this with dominoes, which I couldn't do it because I don't have enough dominoes, but if I were to make it with dominoes, what this spacer does is just basically count as a delay signal, right? So if I have this little thing, oops, why did I do that? Okay, if I have that little thing, basically, and it goes all the way like that, then I'll give it time to be interrupted here, right? See right here. So if it's interrupted, then that's good. Then I can make it like a 0. Okay. And then I have all that represented also in the Python code here. And I have a little bit of a demonstration about how I kind of flipped it over. It did not work successfully, unfortunately. But I still think it's pretty cool to kind of see how it would work if I were to, I guess, flip it accurately. So let me see if I can show it. I think the sound is also playing, so that's good.
So my mental calculations are telling me that if I add 1 0, 1 1, and 1 1 0 1, I'll get 1 1 0 0 0. So therefore, I should flip both these two. Let's see. Okay, that's flipping over. Okay, so then that will...
It doesn't technically work super successfully, but I mean, I think the concept's pretty cool. And if I were to do it with dominoes, then definitely it'd probably be probably work, but then also it would probably fall over a lot faster. Yeah, but essentially all it takes is just a bunch of XOR gates and AND gates, and that's it. I mean, that's pretty much just the entire thing. You just take it and just build a bunch of it. I mean, I guess that's what computers are in the first place. Yeah, that's pretty much it. And these are my references. I got inspired by a video by Numberphile, if any of you've watched that, where he basically does this with actual dominoes, and he added 1 plus 1 together. And I thought, I was like, oh, maybe I could try that with 4 plus 4. But I mean, obviously that's going to be a lot more dominoes.
Okay, that's exactly on the mark. We can now move into 4 minutes of questions.